Hello everyone, welcome to today's video. We're going to be talking about exponential and logarithmic models today. So this is going to be wrapping up our section here on exponential and log functions. So we'll look at some exponential models to start off with. We'll look at continuous, growth, and decay, and we'll actually compare that to the discrete models that we've seen before. We'll look at some half-life applications, and then we'll look at the doubling formula, more or less as a way to compare the continuous and discrete models to be able to see how they're connected. And then we'll take a look at a logarithmic model as well. So we'll start off here with the exponential growth and decay models. So on the left-hand side, I have the discrete models, which means that we're looking at discrete units of time. Like every year, we will add 11% interest to our bank account. So that would be something that's compounding yearly, meaning during that year that we're waiting, the value is staying the same, and as soon as that year is over, then we add that 11% increase or whatever. So that's what we mean by discrete models. There's these discrete units of time where the exponentiation is happening, and then we have continuous models, which means that's something more like bacteria growth or something where, you know, as time is going, we might know that it doubles every, I think this problem says every hour or something. But certainly it's not just doubling every hour on the hour. There's some continuous growth that is going on there. So we have this model as well. So focusing on the discrete model maybe first, we've seen something like this before, where we have r being the either rate of growth or decay, and then t is our time, and that's the discrete time, per hour, per minute, per whatever that we're looking at. So we have our models here. If we have growth, then notice that a naught, I didn't write it down, but that's always the initial value. The value in front is the a naught. And then we have 1 plus the growth rate, if it is growth, or we have 1 minus the decay rate if it is decay. So those are the differences in those two formulas there, but we're always starting off with 100% of what we are starting off with plus whatever the growth rate is, or 100% of what we're starting off with minus however much we're losing per unit of time. So there is our discrete model. This often can be viewed as just, that 1 plus r, 1 minus r is the base of this exponential function times some initial value. And then over here, what we haven't quite seen yet is this continuous model. Here, k, which is up in the exponent here, that is going to be our growth or decay constant. And in this case, if k is positive, we'll have growth. If k is negative, we'll have decay. And remember, e is just a constant number. It's about 2.718, blah, 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 blah. But that is just some number that's being raised to this growth constant or decay constant times the unit of time. And now it doesn't have to be necessarily a discrete unit of time. We can just plug in any old time since this is continuous growth. So that's what the formulas look like here, and I want to dive in a little bit more about this kind of discrete versus continuous thing in terms of this example. So if we're thinking what this says here, a population of bacteria doubles every hour, find a formula that models the growth of a culture starting at 10 bacteria. So kind of what I was thinking about and saying before is that if I try and draw a graph of what's happening, maybe try that one more time, I think it can be a little bigger. If I want to draw a graph of what's happening, after 1 hour, after 2 hours, after 3, 4, 5, etc. So this will be the number of hours down here on the x-axis. And then on the y-axis, we'll have 3, 4, 5, 6, 7, 8. We'll have the number of bacteria. So we're starting with 10, and then it'll double. So there'll be 20, 30, 40, 50, just marking some units here. Okay, so if I'm thinking about what this discrete model says, it says that when we start off, there will be 10 bacteria at time 0, and we know that after 1 hour, it will double and it'll go up to 20. So that's what we mean in kind of this discrete sense, that we don't necessarily know what's going on during that time. This will have some continuous growth, and we'll look at that next. But just kind of thinking discretely here, we know that after another hour goes by, after a second hour, well, then it'll double again, and it'll go up to 40. So after 2 hours, we are up at 40. And then maybe we don't quite know what's happening between hours 2 and hours 3, but it happens, and then, oh, whoops, all of a sudden that jumps up to 80. So we can see it's doubling every hour here. If I finish my graphs, and then even continues growing after that for the next hour. So this is what we mean by like discrete intervals, where things are doubling on the discrete units of time here. But certainly there is some number of bacteria growing in between one. So if let me write down what this formula looks like before I get ahead of myself here. If I wanted to write this formula down using the discrete model, either one will work. In this case, we have A of t is going to be equal to the initial amount, which is 10. So A naught always gives us our initial amount. We're talking about continuous growth here, so we want to add the growth rate. So this is going to be 1 plus, so what is happening is it is growing by 100% every hour. Hopefully that makes some sense. If you're getting 100% back of what you started off with, then that is going to be 100% growth rate. And we'll raise that to the t power, and I could simplify this a little bit. This says 10 times 1 plus 1 is just 2 to the t. And hopefully this makes some sense, because if things are doubling, then 2 to the t is the doubling function for time t. And then we have our starting amount here. So hopefully this is connecting some dots and seeing that this is actually things that we've looked at before. And this is a formula that we could use. Now, like I was starting to say, there is some values that are going to be happening like during that first hour. So it's not that just after the first hour, it just magically doubles from 10 to 20 and nothing happened during that first hour. It's like certainly there was some growth happening during that first hour, and certainly there was some growth happening during that second hour and during the third hour. And we can see that we get this continuous function here, exponential function, that is going through all of the points that we expect it to as things are doubling. So let's think about what this might look like. And actually, I'll just tell you right now what it looks like, and we'll see in a future page here maybe how we can compute this. But A of t can also be represented. The initial amount is still the initial amount. A naught is always going to be representing the initial amount. Now this will be E. Now what is a little bit weirder here is finding these growth constants, because it doesn't necessarily always come straight from the problem or from things that we're told, and we need to compute what the value is. For right now, I'll just tell you that the growth constant here is going to be the natural log of 2, and then we multiply that by t when we're done. And we'll see something like this in a little bit as well, but maybe to just further convince you that these say the same thing, that those, whoops, not equal, that those are equal to each other, let me remind you that if we just focus on this portion of the equation, e to the ln of 2, well, those are undoing each other. If we have the exponential function e and we have a natural log plugged into that, those are undoing each other, and that is just turning in to 2. So if I rewrite the rest of the function here, we still have 10 times 2 being raised to the t, which is exactly what we have right here. So these are saying the exact same thing, whether I write it in the discrete form or the continuous form. We can see that we can actually turn them into each other, so they are saying the same thing here. So we have options. Sometimes it just depends on which formula you would like to use, if you can figure out the growth rate. Most of the time I'll just be using the continuous model, because it is always going to work for us and be a little bit nicer than the discrete model, but we might use it to play around with in some future pages, some future slides here. So next we will look at half-life, which is modeling exponential decay. So the length of time it takes an exponentially decaying quantity to decrease to half of its original amount is called its half-life. So what that's saying is we start with some initial amount. We'll do, we're just going to get an example, or a formula in this first problem. But what this is saying is, if we start with 100 grams of, let's say, carbon-14, then how long does it take to get down to 50 grams? And then how long will it take that 50 grams to get down to 25 grams, etc. So each time, each half-life, there will be half the initial amount left over. So what we have here is a relationship kind of coming from the formula, A sub t, or A of t, equals the continuous model here. But we know that when t is equal to the half-life, that the initial amount, this is whatever we started with, will be half the initial amount when t is the half-life. So we get this nice relationship here where we can actually use this to solve for that growth constant, the decay constant, k in this case. And we should get a negative value for that there by things that we saw on the previous slide, since this is decay. So we will look at this next example here to use what we know about half-life in this relationship. So it's telling us that the half-life of carbon-14 is 5,730 years. You'll see that number pop up a lot if you're dealing with the half-life of carbon-14, because that is the half-life of carbon-14. So we want to express this amount as a function of time. So this is essentially asking us to find the formula, the amount at time t of carbon-14. So let's use the relationship that we have here. We know that at the half-life, at 5730, that whatever initial amount we are starting with, we don't need to know what it is, that e to the k, and now the time here is the time that we're plugging in. It is the 5730. This should be equal to 1/2 the initial amount. So because we are plugging in the half-life, we know that the initial amount should be half after that amount of time has gone through. So hopefully that setup is making some sense there, and why we will always have 1/2 the initial amount at the back end here. And now we can just focus on solving things from here. To solve for k. That's what we want to do. We want to figure out what our decay constant is, and then we can use that to put it together to get the entire formula. So we notice straight away that we could divide both sides by a naught. Those will cancel, and those will cancel. And then at the next step here, we have e to the k times 5730 is equal to 1/2. Let me maybe move that down just a little bit. Okay, at this point here, we're trying to solve for k. It's trapped up in an exponent, so the way that we can deal with that is using logarithms. So we will take the natural log of both sides here, the natural log of e to the k times 5730 is equal to the natural log of 1/2. Well, this left-hand side, we have an exponential function being plugged into a natural log function. Those are undoing each other. What we will have left here is just k times 5730 equals the natural log of 1/2. Now we can divide both sides by 5730. And we've got that k equals the natural log of 1/2 over the half-life, which is 5730. Now, doing that work is important, and it's good to know how to do that on the spot, so you could always solve for k in weirder scenarios that maybe aren't necessarily a half-life. But this does give us a relationship for k that we'll always have. It will always be the natural log of 1/2 over whatever the half, I'm just calling the half-life h in this case here. I'm actually not going to leave that here because I don't want you to just memorize some formula, but I want you to understand how to get this if you had to. So we know what k is now. Now we can go back and actually write the formula that we're asked to write. So this is going to be a of t is equal to whatever initial amount of carbon-14 we're starting with times e, and this is going to be raised to, now our k is going to be written very weirdly. It's going to be the natural log of 1/2 over 5730 times t. So a very maybe uncomfortable thing to write, but this is an exact, precise answer here. Now there could be some simplification we could do on the e because there's a natural log up there, and maybe we'll explore that in a future slide here. But for now, we'll just leave that as our solution, and here is a perfect formula. We could always approximate what k is as well, but whenever you approximate and plug things in, you will get errors farther away from your answer, and we don't want that. So this is a perfect exact solution here with that weird value of k, but it is exactly what we want. Whoops. All right, taking a look at this example here, similar to the previous one, we had a half-life. This is a doubling rate. So now not talking about a quantity being cut in half at some interval. Now we're talking about some quantity doubling at some regular interval. So the time it takes for a quantity to double is called the doubling time. And I'm going to represent the doubling time with just this variable d so that we can keep track of it a little more easily here. And if the doubling time is known, then we can get that the k value will always be 1 over d times the natural log of 2. This also just says the natural log of 2 over the doubling time. So maybe let me convince you that this is what I say that it is. So just to do a little bit of work here, if I'm looking here, what this is saying is that when I plug in the doubling time to this formula, whatever initial amount I have should be doubled when we're done. So when we plug in d, the doubling time, the initial amount should be doubled. So hopefully this setup here is making some sense. It is what we're going to use, and if we focus on this portion here, then this will say I can cancel those a naughts like we did before, and I've got e to the k times doubling time is equal to 2. I take the natural log of both sides. Well, do that in another step here. I'll take the natural log of both sides. Here the ln and the e are undoing each other, and we just get k times d equals the natural log of 2. And if I multiply both sides now by 1 over d, I could divide by d, but I'm trying to get things in a form here that'll be helpful in a minute. Those will undo each other, and we've got k is equal to 1 over d times the natural log of 2. So there we go. We get what I promised that we get. But now I want to use it in this next portion here. So let me get rid of what I just wrote here to create some space. So now I'm just going to plug in this value of k for our value of k over here. So this looks a little bit weird, but I'm just plugging in that weird value of k. And I'm going to do some simplification. So what this is telling me is I'm going to have a naught times e, and I can use my properties of exponents here, where I can think about taking the coefficient in front of the log and putting it in the exponent. So now I've got the natural log of 2 to the 1 over d times t. A little better. Times t. Well, if you notice, this portion right here is an exponential being raised to a natural log, which means that those are inverses, those are undoing each other. All we get is just the argument here. Just what we're plugging in initially is going to be our initial output as well. So all this here just says 2 to the 1 over d. The a naught is still the a naught, and it is still being raised to the t. So I can clean this up a little bit more, and I get that this is a naught times 2 to the t over d. So this is going to be our formula for the doubling. So I could have kept it in that exponential form and just used that kind of natural log and plug things in there. But we get this doubling formula, and hopefully it's not a surprise that 2 shows up as the base of the exponent, because that is going to double things for us. But when the doubling time is in some other weird unit, like in this first example that we're going to see, we see that the doubling time is every half hour, so it's every 30 minutes. That's not just a single unit of time. So you might notice that there's this kind of division that's happening up in the exponent where we're dividing the time by the doubling time. And I mostly just wanted to convince you of why that happens in this formula. The formula that we get now is, just to rewrite it, a of t equals a naught times 2 to the t divided by the doubling time. So that seems like a weird formula. Why are we going to divide t by the doubling time? Other than when you plug in the doubling time, you get 2 to the first, which is exactly what we want, which seems like kind of a lazy excuse. So I wanted to give a little bit more of an algebraic excuse for why we get that t is divided by the doubling time in this formula. So now we're free to use it. We're being told in this problem, like I said, that d in this case is going to be 30 minutes. So we know that every half an hour, every 30 minutes, this culture will double, and we know that the initial amount is 1,500. And now we can use our new formula here to get 1,500 as our initial amount times 2 raised to the, we want to know what, oh, I'm sorry, let me go back. What we want to find here is A of 20. What we're asked is to find the population after 20 minutes. So if I'm plugging 20 into our formula up here, our initial amount is going to be 1,500. And then we want to do 2 raised to the 20 minutes is the time that we're plugging in, and we want to divide that by the doubling time. And this gives us actually where's my calculator? I probably should have done this at some point. I'm sure it's on a piece of paper around here, but I need to plug this in as well. So this is going to give me 1,500 times 2 to the 2/3, reducing that 20 over 30. So if I do 2 raised to the 2 divided by 3, I get 1.58, blah, 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 blah. And I'll multiply that by my initial amount of 1,500. And we get that this is about 2381. And yeah, we round down to 81. So this tells us that if the doubling rate here is every half hour, then after 20 minutes, an initial population of 1,500 should become 2381. And that makes intuitive sense to me because after 30 minutes, we would expect to have 3,000. So after 20 minutes, we're somewhere between our initial amount and the doubled amount. So we're not quite there yet. So yeah, I'm feeling good about this one. But kind of the moral of the story here was just to be able to kind of look at how we get this doubling formula, and if you have to do something similar and you notice that you're dividing the input value, the t value here, by some other value, that's the reason why. And it's just because these things aren't cut into single units that we're plugging in, but some either portion of a unit, a half hour is a portion of an hour, or it's a multiple of the minutes that we have. We need to kind of undo some things there. So. All right, let's look at another application here. So this is a logarithmic application. So all the previous ones have all been exponential applications. Here's a log application. And we're looking at the pH scale for acidity being defined by this relationship. So this is just the way that pH is defined. You may have heard of the pH scale, and it is the negative log, and since it's not indicated, that's base 10, of this weird symbol, H plus, where H plus, I could be saying that wrong, maybe there's a different way to say that, but I'm just calling it H plus, is the concentration of hydrogen ions measured in moles per liter. Now, a mole is something like 6 times 10 to the 23. It is an extremely large number, so we'll see here when we do this example that we will probably get scientific notation for our solutions as well. So this is just a big unit of measure. It's saying that there are essentially 6 times 10 to the 23rd, which is just 6 with a bunch of zeros at the end of it, of these hydrogen ions per liter of whatever substance we have. So for this first one, we're asked to find the concentration of hydrogen ions for pure water, which has a pH scale of 7, which I believe is right in the middle. So water should, I guess, is not acidic nor basic, so it should be right in the middle. Correct me if I'm wrong. But what we want to do here is find the moles. So we know that the pH is equal to the negative log of the concentration of ions. And we also know that this should be equal to 7.0 in this case for water. So if we focus on the right-hand portion here, I can multiply both sides by -1, and I'll get that the log of H plus is equal to -7. I'll just keep that as -7. Since 7.0, we can just write -7 to make things nice here for us in just a second. But now I can use base 10, and I can raise base 10 to both of these expressions. So sometimes we say colloquially, we'll 10 both sides, we'll base 10 both sides here. And then sometimes I like to just rearrange where that equal sign is. So now that it looks like 10 raised to the log H plus equals 10 to the -7. So if I rewrite this now, the reason that I'm raising both sides to the 10, or I'm base 10ing both sides, is so that these undo each other, and I just get the number of ions here, the H plus notation. And this is equal to 10 to the negative 7. So if I wanted to write this in scientific notation, I could write this as 1.0 times 10 to the negative 7. And if I wanted to write this as a decimal, then I would have to move this decimal 7 places to the left, which is going to give me 6 zeros and a 1. So this is a very small number. Either of these are fine. It's a very small number, but we're trying to find the proportion of this number, so things are balancing out here for us. Even though that seems like a very small number, it's actually pretty big in comparison. Okay, so that is how to find the concentration of hydrogen ions for pure water. Next, we'll look at drain cleaner, which has a pH of 13.3, which is very, very basic. Yes, I think basic is the closer to 14. Correct me if I'm wrong. But we'll do the same thing here, where we know that the pH is going to be, just using the formula that we're given, negative log of the hydrogen concentration. And here this is equal to 13.3. So we'll do just like we did before. We'll multiply both sides by negative 1. We'll get the log of the hydrogen concentration is equal to negative 13.3. And just like we did before, we will base 10 both sides. And then I will redo where my equal sign is. That's not something that you have to do, but I think that is visually pleasing to see what's going on here. So the left-hand side is just turning in to that H plus notation. And on the right-hand side, I have 10 to the negative 13.3. Now, I don't have an easy way to turn this into scientific notation other than putting it into a calculator because of that 13.3. So I will just put that into my calculator. And I have 10 raised to the negative 13.3. And I get that the concentration of hydrogen atoms is 5.01 with some change times 10 to the negative 14th power. So again, it seems like that's a very small number, but once we multiply it by moles per liter, we get that the number of actual hydrogen ions is going to be pretty large. So there we go. There is our, whoops, I didn't, oh no, that is my answer. There it is. There's the answer to that one. That is an application just using some logs. There's some different applications that use the log scale, like the Richter scale, and some other ones that show up in the homework. Speaking of the homework, it is time to practice. So that wraps up this video for us. I will see you in the next one. If you have any questions along the way, please let me know. I'm always happy to help.